Hi. This is the third meeting organized by you Price, to which I'm invited. I guess the future wave function is coming from either Reykjavik or Alaska, if you care to invite me to the next one. But it is interesting to think how in each of these conferences, and they span over several years, I presented different views and I shared with you the changes in my thoughts in my work. So this is going to be the case too. Last time when we were in Cape Town, just let me mention the sources from which inspired me. The Wheeler and Feynman absorber theory. Aharonov's two-state vector on which we draw now, Kramer's transactional interpretation, and of course there were adversaries which were no less inspiring. First and foremost being Neil Price, with whom I take exception on almost everything, but he keeps for some reason inviting me to his conferences. Humphrey Appleby once said why he never attended Cambridge. It's not politically correct, so I won't mention his argument. But Lev Weidman is never politically correct, and he's now in Cambridge, and he has been another very inspiring adversary. And there have been Nicolas and Ruth, and I thank all of them. When we met last time in Cape Town, I was very enthusiastic because I believe that I had a very strong experiment which attests to something very deep within the TSVF. The idea was to take Bell's experiment and combine within that experiment both weak and strong measurements. And the idea was this. Actually, Bell's proof is a proof of the emptiness of the past. That is, you cannot ascribe the correlations, the EPR correlations, to a common cause. There couldn't be such a cause to effect for the free choice of the experimenter. And then we believed that we can do something very neat here. Let Alice perform on these pairs of particles, EPR particles, perform weak measurements along the three spin directions. Let's then, and even repeat them, let her ride them on a rock, and then at evening, much later, let Bob, and you will get results which seem to be meaningless. Then at evening, let Bob make a free choice of the last moment, whether he wants to measure alpha, beta, or gamma when you're talking about photons. And then when you get his results, this is last minute choice, and you slice them, what is up, what is down, which direction he took. And you take the dividing line and shift it on the rock. Then it turns out that the results of the weak measurements that Alice obtained at noon, which appear to be meaningless, somehow anticipated, lo and behold, the free choice that Bob is going to make at the evening. And that was pretty thrilling. Apparently, there was here a strong kind of, I wouldn't say evidence, but support to the claim of the TSVF that the future somehow affects the past, although in a very subtle way. I was very happy about that, but then dissenting voices among peers began to come, and people said, that you have to be able to explain everything that is explained by the two-state vector formalism by the one vector formalism, such as, and here is the proof about which I felt very strong. I was hoping that the emptiness of the past would preclude, or not preclude, but make any one vector formalism to look a bit dubious. And perhaps I was asking for too much. I'm not sure I'm not sure yet. And people told me actually that weak measurement, according to the one vector formalism, weak measurement is not that weak. And there is some spoiling. What my argument was that have the origin of the correlations be in the weak measurement, they would spoil the correlations of the evening. If you make measurements, if you take an EPR pair, make your own measurements, and then wait for Bob to make his measurements, which are free choice, you're going to ruin most of the Bell effect. And my claim was, we don't see any such ruining of the effect. So it's very likely that the influence goes from the future to the present or to the past, from the strong measurements at evening to the weak measurements at noon. Then upon calculation, people said, don't be so sure about that. The amount of spoiling that you see in the measurements of the evening, although you can ideally make it very small, is just the amount that you need to make the bias such that the slicing, which I described here, which is a very simple operation, gives you the magic. Alas, it turned out that you can't make the one-vector formalism look ridiculous or cumbersome or something like that. It is just a matter of aesthetic appeal. Do I concede defeat? Not so fast. I still believe that a Bell-like proof, perhaps with continuous outcomes, remember that when you are doing weak measurements, you don't have discrete outcomes, spin up or spin down, but you have all the things in between, plus some strange results. I still believe that a Bell-like proof will be attained one day, which will do the magic that I'm hoping for, but for the time being, I can't show it. What I can show is the following thing. I'd like to take another brainchild of the TSPF, and that is something strange to which you can refer to as negative momentum, and which has been referred to in earlier talks. And see that when you combine that insight with the idea of effects coming from the future, the combined result is still, first of all, beautiful, simple, and may even suggest some ideas for experiment. So here it goes. You probably know the story, which has been presented so many times. This is the story of the particle in 3 boxes. You make a pre-selection, and then you split it into 3, such that it goes into 3 boxes. Then you don't open the boxes, you reunite the 3 parts of the wave function, make your post-selection, and if you got this result, then you can claim that what happens is that the future state vector affects the content of the 3 boxes in the following way. If you open one of the boxes, you are supposed to find the particle in that box. If you open the second box, again, surprise, you're supposed to find the particle in that box. And if you open the third box, you would get something which is not that the particle is not there, but something which people would describe as the particle is really, absolutely cannot be there. Just don't even think about it being there. And I believe that I can equate this moment with what Dirac did when he trusted the formalism upon studying the Schrödinger equation. He said, trust the formalism, and if you get something as strange as an antiparticle, an electron with a positive charge, then probably it is there. And people laughed at him, but then he turned out to be correct. Basically, this is what Aharonov did. He said, if I get this minus sign, I should assign it to something physical, and this cannot be the charge, so what is left is the momentum, or actually even the mass. And this already should ring beautiful to you, because the idea that negative mass, negative energy, negative momentum is akin to something coming from the future is something that is familiar for everybody interested in the CPT, in all those symmetries in which space, time, and parity are deeply related. But this is just an intuitive thought. What I was interested in was the following thing. And this is another version of the particle in 3 boxes, although it's only particle in 2 places. suppose that you pre-select a particle, say a photon, make a certain pre-selection, and then let it go through a Mach-Zehnder interferometer, and then reunite the two halves of the beam and make a post-selection. Then, upon getting the rare condition that you want, you will find out, and you make now weak measurements. These mirrors are not making strong measurements, but weak measurements of where the photon did go. So by the receiving momentum from the photon, they tell you whether it went to the right or to the left. Of course, because this is weak measurement and very noisy, in some of the cases, the mirrors will turn out to get a momentum at the negative direction that is jumping inside rather than outside, which we would of course ascribe to mirror noise. And it is again, according to the TSVF, the post-selection, which would show you that under those cases of the post-selection, you do have a slightly larger probability of such inner jumps, which indicate something similar to that not anti-particle, that non-particle or by no means particle in the third box. That is that the minus sign would be assigned to something as physical as the momentum, and you would be able to argue that the mirror has jumped inside due to the negative momentum, in order to account for this strange thing that, according to the TSVF, has to occur between pre and post selection. The interesting thing is that even before you do the post selection, you find something interesting, an interesting correlation between the two mirrors. And here is the thing that made me a bit excited. Our failure to prove that in the earlier experiment of the EPR, our failure to prove that there is really an emptiness of the past and that you are not contaminating the experiment was that it was possible to show that even at the time that Alice writes her weak measurements, the outcomes of her weak measurements on the rock, it can be shown that there are slight correlations between them. So, I went to the extreme and I even divide an experiment in which there is Alice, Bob, and there is even an Eve who grabs some of the pairs of the particles, make full measurements on them. Actually, no Alice. Let there be only an Eve and Bob at the beginning. And then there is an Eve who grabs the pairs of particles on their way to Bob. And then she makes full measurements on a very small number of them. That is enough for her to pollute the outcomes of Bob in such a way that the experiment which I described in such a bravado earlier would give very similar results. So then people would say there is nothing coming from the future. You only managed to create a kind of subtle pollution in which you did not ruin the EPR correlations, but you just gave the impression that something which is coming from the future is affecting your present results. Do I make myself clear? I want to make this disappointment be made clear, such as opposed to the enthusiasm which I showed in the last time when we met in Cape Town, in order to show why I went further in search for a better indication that there is a very deep truth within the TSVF. I was believing that because of the emptiness of the past, there couldn't be a case, it would be very hard to make a case that the present is affecting the future, because I thought that the Bell inequality as we use it now is robust enough to show that the past is empty. There can't be anything there such that the effects have to come from Bob from the evening to the noon. And it looks like I failed. And I took it to the extreme, to the case of somebody actually deceiving you. There is an Eve who actually captures some of the small number of the particles, makes full measurements on them, and then at evening when Bob is making his choices, he will see slight disturbance of the results, not enough to suspect that there was something going on, but then Eve may come later and say, wow, my results anticipated yours. I hope that I'm making myself clear about this disappointment that I had in order to show you why I wanted to go further. it is very intuitively, it is very appealing to say that the choice made by Bob at the evening is somehow affecting in a very subtle way the results which Alice wrote on the rock, carved on the rock at noon. And people who support, and we heard such talks earlier, people who support the TSBF would say, you would admit, and we heard Nikolai actually saying that following Lev's talk, you heard people saying that there are some effects that they would never dream about them had they been thinking along the one-vector formalism. So that means that the two-vector formalism has some truth in it. I also think so, but playing the advocatus diaboli, I can say the following. There is the minimal action principle of the Maupertuis, which has many, you probably remember Feynman's famous lecture as a schoolboy when his physics teacher told him about that principle. And he was very thrilled about it, and this is something which affected later his revolutionary thinking. Nobody would say that because, imagine you have a light ray being reflected, and then you know at the end where it is going to be absorbed. Nobody would say that because it is easier to calculate backwards from the place where it is absorbed, that there is some ontological truth to the least action principle, such that we will argue that influences are coming from the future. Somebody may say the same thing about the TSVF, and this is why I wanted to go further, and this is why I went to another brainchild of the TSVF, and this is the negative probabilities being assigned physical meaning such as negative momentum or even negative mass. So here it is. This is the experiment, which I'm not describing in full. It is similar to the 3 boxes experiment. You take a photon, make a pre-selection, then you let it go through a Mach-Zehnder, and the pre-selection has some effect on what happens within the Mach-Zehnder, and then you reunite it, finish get the interference effect, and then make the post-selection, and you find out that in those cases in which you got the post-selection that you desired, there is a larger number of cases in which the mirror was apparently got a momentum which made it, rather than jump outside, jump inside, as if the photon was pulling it rather than push it, which is very exotic and rings very truthful if you think about the CPT or other similar ideas in physics. But can we gain from it, can we squeeze out of it something even stronger? And here is the point. I would argue that in this case, if you want to be a one-vector formalist, and a very ardent one, you will have to do the following. Say, oh, okay, so there is negative momentum, there is negative mass. Everything, just don't give me this crap about things coming from the future. I believe that we can come now to push the one-vector formalism to the corner in which it would willingly admit strange physical effects, just in order not to accept influences coming from the future. And here's what we do. You remember my disappointment from the EPR experiment. Even at noon, when Alice carved her results on the rock, which looked meaningless, if this is a very large ensemble, you will see that there is a very slight correlation if she measured the right-hand particle and the left-hand particle according to the sigma x, sigma y, or sigma z, or I use here another notation, alpha, beta, and gamma. You will see a slight correlation of up, down, up, which means what Ruth Kastner has been telling us all along, and I hated to hear that. Weak measurements are not that weak. So the kind of influence that you see goes, you still say that, goes from the noon to the evening. And I almost had to concede defeat. But then that defeat seems to be interesting in this case, because even in this case, when you make weak measurements of the mirrors, you see that there is some interesting correlation between them. Very weak, you will need huge ensembles, but then something strange is happening. May I call it a kind of measurement effect? Because here what goes on. Suppose that I place 2 mirrors, and this is something that I will elaborate a bit later. What makes a weak measurement in this case? So first of all, we have to review what makes a strong measurement. In order to have a strong measurement, you want to get the change in momentum you have to pay the price for the macroscopic object, for the mirror, to be uncertain in terms of its position. So the uncertainty relations hold not only for the photon, also for the mirror. The mirror must not have a precise position such that its momentum will be very precise. It is zero before the photon has hit it or has not hit it, and then you see whether it gained momentum or not. So how do you make the measurements weaker? You make the measurement of the mirror's position more and more precise, such that its momentum becomes more and more uncertain, and then measurement begins to be weak. The more precise you are in measuring the position of the mirror, then you're gradually shifting from strong to weak. So this is what I want to do with you. Gradually shift from strong to weak. We begin with mirrors which have an imprecise position such that their momentum is clear. It is zero before, and then we see whether it is zero after or has gained some momentum. And then we are making it weaker and weaker until we have a weak measurement. What do we get? As long as the measurements are strong, noise is minimized. Okay? So we leave the position uncertain such that the momentum is very clear, it is zero. Nearly all outcomes are accurate if there is no noise. And of course, they are positive. You will never get any you will never get any mirror just jumping inside because the photon is hit it. So far everything is agreed. And of course, they are going to be correlated. If this has been pushed, the other will not be pushed, and vice versa. Now you're making them weaker. That means that noise is nearly maximized. So the mirror gets a lot of momentum changes regardless of the photon. So you're never sure whether what you observe is due to the photon or due to the mirror's noise itself. It's only over large ensembles that you do the slicing operation that we described and manage to squeeze out the signal out of it. Then, of course, nearly all outcomes are random because there is much more noise than signal. And then more and more outcomes are becoming negative, such that when the measurement is absolutely weak, then you have an equal number of cases in which the mirror is jumping inside rather than being pushed by the photon to the outside, and nobody is going to be excited of that, right? Because you say this has nothing to do with the photon. This is the component of noise contributed solely by the mirror, nothing to do with the photon. So don't worry about that. This is what the one-vector formalist is going to claim, and we're going to push them slightly to the corner where we want to manipulate them there to be. And then, of course, they'll say nearly all outcomes are uncorrelated. So from these together, it follows that all negative outcomes must be random, come from the mirror and not from the photon. Therefore, all the accurate outcomes are correlated. You will find correlations only between the accurate measurements, which are very few. Right? Wrong. And let's put it graphically. So here is my measuring apparatus, and I shift it from strong to weak. So here I have two outcomes. Here I have one particle, here I have another particle. These are the correlations between them. And I begin to shift it to make the measurement weaker and weaker. Okay? So there is some noise going on in. The signal shrinks in favor of the noise. The correlations become weaker, and we don't expect, and what we see in the correlations, we expect to see only the signal. The correlation is only between the signals, not from the noise. God forbid any correlation which involves the negative jumps of the mirror, right? Wrong. It turns out that in some of there is a slight correlation involving even the cases in which the mirror jumped inside. That is, you can say that when one mirror was pushed too much outside, then there is a slight increase, slightly larger probability for the opposite mirror to jump inside. And because they are connected by the photon, here is a case in which the one vector formalist can claim, in order to avoid anything coming from the future, that it is the photon who impinged on the impinged on the mirror is the agent that has made it jump inside, affecting a sort of a negative momentum on it. And now we understand this is almost trivial. Signal and noise are not distinct. In classical physics, they would be distinct. You will be able to tell them apart. But in this case, we have a mirror which is a quantum object, although it is macroscopic, and we have a photon which is a quantum object, so they become entangled. And it is the ignorance about who is the parent of this effect that gives you now the effect. That in some cases, something which belongs to the realm of noise crept into the signal, and in this case being something as exotic as a negative outcome. Where does this take us? I was going to present now a work which we presented a month earlier in Torino about the quantum oblivion effect, which I'll now try to reconstruct it. It goes something like that. This is a work which I presented with Eli Cohen, and hopefully soon we will have a paper. We are very thrilled about this work because actually there is nothing revolutionary in it. It only explains things that we knew all along, but then gives them a very neat and simple explanation. So here it goes. Imagine the following case in which you split a particle and an antiparticle through a beam splitter such that one half of the wave function of this antiparticle crosses the two paths of this particle. So something interesting is going to happen here. And then later you can either use interference or make them return in order to see what happens. So in some of the cases you will get, and I'll skip the mathematics now because I don't have the presentation, I'll show it only qualitatively. In some cases you may get an annihilation here, end of the story. In other cases you will not get an annihilation here, there will be a certain period which we call the critical interval, and you will get an annihilation here, end of the story. But in the rest of the cases you will not get any annihilation, and now you have a very interesting case in which this particle, say if this is the positron, and this is the electron, remembers what happened. Because when you either make an interference or make it return, it may sometimes come to here. So it has changed, its momentum has changed. Whereas this particle knows nothing of what happened. It has been superposed, it remains superposed, there is no physical trace left here. Which is kind of strange because what law are we talking about from classical physics? Interaction between two parties, one carries the effect and the other doesn't carry the effect. Doesn't strike you as odd? This is Cambridge, 1966. Isn't there a law which says that this can't happen? What am I talking about? Let me repeat it.
So what is the explanatory expression?
You have a particle and antiparticle. Half of this wave function crosses these two halves, and there was no annihilation. So the momentum of this particle has changed, that this positron, right? If you now place two mirrors and want it to come back, you know that it is no longer here. It is only here. Whereas here, you still remain oblivious about where the electron is, or the electron is. So the momentum of this electron hasn't changed. The momentum of this positron has changed. Am I correct? Does something here strike you as odd? Cambridge, 1966.
Why 1966?
Sorry, 1666. here now after I made the correction. Newton's third law. So we called it quantum oblivion. One particle remains oblivious of the interaction, whereas the other carries its effect, and even in a dramatic way. What is happening here? So in order to probe what goes on, of course we find out that what we call, this is a kind of interaction-free measurement. Now, is this something very rare, something exotic, some nice play? No, we argue that this is part and parcel of every interaction-free measurement, but perhaps of every measurement. Because what happens is that through a very brief period, they are entangled, and then they become unentangled. Not disentangled, unentangled. There is a complete reversal here. At this time, either the photon is here, either the positron is here and the electron is here, or the positron is here and the electron is here, they are entangled. Once there has been no annihilation here, and of course you need a detector here to find out whether a photon came out or not, then you have this interesting case in which only one of the parties of the interaction remembers it, carries its effect, while the other remains oblivious. Why is this so important, and why is it ubiquitous rather than just a nice play? Because we have to recall, and luckily I mentioned it earlier before the presentation was turned off, we have to recall what is a measurement. When you make a measurement in a Mach-Zehnder interferometer, so here you have a beam splitter and here you have two mirrors, in order for the mirror to tell you whether it was hit, whether this mirror or this mirror were hit by the photon, you have to make them imprecise, you have to make their position imprecise, such that their momentum is zero. Such that when the photon hits them, either the whole thing moves, such that you don't know its position yet. You only know that it gained momentum. Okay? Now, do you realize that I'm talking about ordinary measurement? That all measurements are actually of this type, that you remain oblivious of the position. So what happens is that there is a very brief period, very brief critical period, in which even in the case of interaction-free measurement, there has been some interaction between the mirror and the photon. They have been entangled, and then they became not disentangled like after measurement, but unentangled, or in terms of coherence, there was a brief decoherence followed by recoherence. And this is something that happens in all measurements. It is only that we make sure not to interfere at that time, such that we have a measurement, either positive or interaction-free. And then we argued that once you make the measurements subtle enough to intervene within the critical period, within the critical interval, you will get some very exotic and nice effects, and interesting effects, and so on. This is the quantum oblivion effect, and which we argue that is part and parcel of every measurement. There is something going on very subtle, which weak measurement, and actually the transition from strong to weak measurement is going when you are actually making the critical period longer, such that you can intervene and you get the interesting cases. What we did here was simply quantum mechanics, one vector formalism without mentioning retrocausality. However, if we put retrocausality into the picture, then we say the following, that there is a brief period in which the photon, which is still superposed, is entangled with the mirror in its front position, then entangled with its other positions until it comes to the last position and then becomes completely unentangled with it. So there is this small period in which all this dramatic thing is happening, giving us the impression that actually nothing has happened. What happens if we make this two vector? I would argue the following, and now I have to lean on my memory without having the presentation. Remember the three boxes. In the three boxes, you see a kind of, again, a violation of conservation, in the sense that one particle is in two boxes, but then that one particle is absolutely absent, more than absent, in the third box. Is it possible, and with this I'm almost done and I want to conclude, is it possible that what happens is that indeed a kind of phantom particle, this is a term coined by Yakir Aharonov, that a kind of such a non-particle or negative mass particle or negative momentum particle goes along the same space-time trajectory of that extra particle which is in the third box, and then gives you the impression that nothing has happened. That behind this nothing, beneath this nothing, there is an anti-something coming from the future. This was the title of my talk on the presentation. So what I want to conclude is with perhaps some thoughts which are more speculations, but they seem to converge towards the same direction. Perhaps it is not a coincidence that both Wheeler and Feynman use negative energy when they talk about their absorber model, and they use destructive interference in order to show why anomalous electromagnetic phenomena do not exist. We don't see waves converging on a source. We don't see a source absorbing a wave and then the other side of the source again emitting a wave. People would say because they shouldn't be there, and Wheeler and Feynman say no, there is a certain effects of negative energies going backwards and all kinds of constructive plus destructive interference which make these nothings appear nothing, whereas there have been something there that has cancelled itself. This is something that was echoed by Kramer. Kramer said that zigzag, exotic zigzag which he described, could be sometimes cyclic, and even negative energy can go back and forth until all boundary conditions are satisfied. Perhaps, and I'm making PR for a new book by Ruth in which she presents a novel version of transactional interpretation, perhaps let's think about the case in which we made two measurements of the photon's position within an MZI, and one of them gave us the interaction-free measurement. What Kramer would argue that the reason why it gives you the interaction-free measurement is that there is another effect coming from the future, from the interference zone, and then pulling somehow that photon to that side. But what if we want to go along the idea of becoming and amend Kramer's model with there is offer wave and confirmation wave? Why not say that equally there could be rejection waves? And the rejection wave, how it is being done, and this is my third and perhaps last perhaps the experiment of the three particle in three boxes managed for the first time to split something that so far appeared together and we did not see it there. If you split, in this case in which you split the particle in three boxes, then you manage to isolate that very interesting box in which there is a negative, weak measurements indicate something like a negative momentum, perhaps negative mass, and this is how the oblivion or the cancellation, either Kramer's or in the ordinary measurement, are somehow cancelled. That is that our world, and let me just summarize the move that I was doing. I was doing advocatus diaboli. I was going with the one vector formalist to the end and denying anything coming from the future, saying that this is just a nice pedagogical device. In order to do that, I believe that now we can point out cases in which in order to do that you have to be even more emphatic about negative masses and negative momenta being involved in any ordinary experiment, just not being seen because it is not properly isolated. There was another thing that I'm sure that was there in the presentation. Yeah, it had something to do with what people are doing with negative energies in black holes and so on, but it takes us too far. So I said, perhaps there are such things. Perhaps the two-vector formalism shows us a kind of sub-quantum world which is even more crazy, even more exciting, even more unbelievable, which present-day experiments are becoming more and more capable of showing it. And I believe that once we do that, and we push the one-vector formalist to that end, and they will admit that there are such exotic things, then we will say, but it's not convincing. Probably there are negative masses and negative momenta, and at the same time, there are effects coming from the future. Thank you very much.